Assalamualaikum and hi again everyone. Today we will continue from the previous video where we will discuss the many different types of valves normally used in a pneumatic system. So I will try to cover as much as possible all these valves as listed in the screen. So there will be pressure regulators, check valve, shuttle valve and control valve and so on. The first valve that we're going to look at is the pressure regulator, where we have talked again. We have talked about this in 13.5, section 13.5 from the text, and these pneumatic pressure control valves are airline regulators that are installed at the inlet of each separate pneumatic circuit. So as such, they establish the working pressure of the particular circuit. Sometimes airline regulators are installed within a circuit to provide two or more different pressure levels for separate portions of the circuit. A cutaway view of an actual pressure regulator. Again, we have discussed the detailed operation of this in section 13.5. Is shown here, right? So the desired pressure level is established by the T handle, as you can see. That's the handle here, which you can turn and establish the pressure level required. So this T-handle will exert a compressive force on the spring. The spring will then transmit a force to the diaphragm, which regulates the opening and closing of the control valve. This regulates the airflow rate to establish the desired downstream pressure. So this is the ANC symbol for the pneumatic pressure regulators. Next is the check valves. So check valves allows movement of flow in one direction only. So these are some examples of actual check valves from industry. So the check valve will shut off instantaneously against reverse flow and opens at low cracking pressures in the forward direction. As shown in the schematic views, the disc seals before reverse flow is established, thus avoiding fluid shock on reversal of pressure differential. Although the design, if you look at here, the design is metal, but lightweight plastic body design with fittings suitable for plastic or metal tubings are also available. Okay, so for this check valve, let's look at an example from the YouTube. There is one nice video explaining the workings of a check valve. This is the Explain Full channel. I will link the original video in the description of my video lecture here.
Check valves. Check valves never get any attention because they are basically set it and forget it type of valve. They only permit flow in one direction, meaning they are directional. In the diagram, the spring compresses the disc, is released from the seal when there is flow. When the flow changes direction, the disc is pressed against the seal. They are best suited for maintaining a separation, for example, keeping hot and cold water from mixing together under the sink, or as a safety net to prevent reverse flow in a fish tank. There's another variation to check valves with a small change. If the check valve seal is extended, then a check valve can be made into a pressure relief valve, where the valve opens and expels excess pressure buildup. The diagram shows preset relief valve, where the spring is designed and calibrated to reduce pressure buildup. The spring compresses till the seal is pushed past the sealing chamber, and then pressure is released until the spring overpowers the pressure and reseals the valve. These valves have saved lives by keeping operating pressure within safe range. And the best part of a relief valve is that the failure occurs at the seal. And when that happens, the relief valve just prevents any pressure from building within the system. So a quick change and you're back up in operation.
Okay, so that's the check valves. Next is a shuttle valve. This shuttle valve is type of valve that has two input ports and one output port, and employs a free-floating spool with an open center action. At one end of the spool's travel, it connects one input with the output port. At the other end of its travel, it connects the second input with the output port. This is actually an OR logic. So it will allow the higher pressure of the input to pass through. So either one that has a higher pressure will be allowed to pass through, and this is the NC symbol. So if you look at this animation, it simply is a OR logic gate where the higher pressure input will be allowed to pass through while the ball will block the other input. The one thing that we should know that the open center action of the shuttle valve, where the arrows indicate the clearance in the center position, okay, this one. As the spool shifts through the center position, it lacks a few thousandths of an inch of blocking the ports. Thus, it is not possible for the spool to find a center position that will block all exhaust action. So that means it will always move to one position or the other. So it will always be either from input 1 or input 2. Okay, so that's the shuttle valve. Okay, next is the two-way directional control valve. Here we can see an air-operated, means air-piloted, two-way pneumatic valve. As shown, this valve is available to operate either normally open or normally closed. The poppet type construction provides a tight shutoff, and variations in the pilot air pressure or mainline pressure do not affect the operation of these valves. So you can see it's two-way directional control valve as shown here. So remember, when we look at the definition of two-way and position, it could be two-way, two position, three-way, two position. So by the definition of way, it means it has two ports. So there's just one and two ports. And this is 2/2 means two-way, means it will just allow one input and one output. So that will be 2, 1, 2, and then the other two means the two position, the two block that is in the symbol of the valve. So this is an example of two-way directional control valve. The next slide is a three-way DCV, three-way directional control valve. This is a multi-purpose three-way or open exhaust four-way push-button directional control valve. The three-way valves are three-port, multi-purpose valve, and any port can be pressurized. The four-way valves may also be used as normally open or closed three ways by plugging the appropriate cylinder port. Exhaust is through two screen ports. The force required to operate this valve is 2.5 pounds. So this is an example. In this figure, if you look at here, you can see the large mushroom head. So it's purposely made that way so that extra heavy-duty operators, especially using the heavy glove hands in stamping press, foundry, and other similar operations, so it allows them to withstand these daily operations. The large rounded button is padded with a soft synthetic rubber, so this is rubber cover, which favors the operator's hand. Okay, next, this is a limit switch. If you recall, we saw a lot of limit switch. It could be electrical, it could be mechanical. So this is an example of a mechanical actuated limit switch. This is a limit switch valve that uses a roller level actuator. These directional control valves are available as multi-purpose three ways or open exhaust four ways. This type of valve is normally actuated by a cylinder piston rod at the ends or limit surface extension or retraction stroke. So at the end of actuator, at the end or at the beginning of an actuator cylinder, once it touches this roller level actuator, it will turn off or it will activate the valve. in whether in the first position or in the second position. Okay, finally for today is the flow control valve. As shown, a spring-loaded disc allows free flow in one direction and an adjustable or control flow in the opposite direction. Flow adjustment is performed by a tapered brass stem that controls the flow through the crosshole in the disc. The adjustable knob, as you can see on the top here, contains a unique locking device that consists of a plastic metering knob and thumb latch pawl. The valve bonnet is scribed with graduations to serve as position indicator for the stem. When the pawl is in the up position, it creates a friction lock on the knurled bonnet and the knob cannot rotate. When the pawl is at 90 degrees to the knob is free to rotate. Mounting in any position will not affect operation. So there's a nice animation video by Mechanis Malar. I will again post the link to this video later on in the description of my own video. But you can see here he's adjusting the flow of the liquid. It could be liquid or gas by the knob on top of the valve mechanism. Okay, so in the last, it is important that the valve be properly sized in the pneumatic system. So if valves are too small, excessive pressure drop will occur, leading to high operating costs and system malfunction. Similarly, oversized valves are undesirable due to high component cost and space requirement. As in equation 13.10, if you recall in the last video, um, we learn how to calculate the flow capacity constant, the CV. So the CV is a direct indication of the size of a valve. Selecting a valve from manufacturer's catalog with a CV value equal to or greater than that calculated from that equation will provide an adequately sized valve. So in this example, we'll try to use that equation to calculate the valve requirement given the pressure of air upstream and the temperature given. Okay, so if you recall, the equation that we are supposed to use is the 13.10 m. We have looked at this before. So the equation is Q is equals to 22.7 CV. Okay, so if you recall, the equation that we are looking at is this one. We have looked at this before, 13.10, where Q is equal to 22.7 CV P1. This is the upstream pressure, and then the downstream pressure, and then the temperature. But in this case, we are given the flow, which is the 50 standard cubic feet per minute of air at 100, that's the pressure. So we want to find CV. So we need to rearrange this equation to solve for CV. If you do that, then you will get CV is equals to Q over 22.7. Okay, so rearranging this equation, you will get this CV, and you can just substitute the values. But remember, the values here, if you look at here, it should be in the absolute values in ranking and pressure in the PSIA, not the gauge pressure. This is the absolute pressure. So we know how the relation between absolute and gauge temperature is given in, if I'm not mistaken, in slide number lecture 2. So as you can see, for the temperature, absolute and gauge temperature is given in this one. So since we are given in Fahrenheit, so that Fahrenheit pressure, that Fahrenheit temperature should be added by 460 to obtain the absolute temperature. And the pressure also, if you recall the atmospheric pressure is 14.7. At zero gauge pressure, the atmospheric pressure is 14.7 psi, so you need to add 14.7 psi to the value given. So that will give us the temperature. The temperature will be 80, which is the Fahrenheit, plus 460. So here you will get 540 degrees Rankine, and the P2 it's 100 plus. This is the absolute PSIA, absolute pressure. So you can just substitute this value. So we have T1, we have P2, and the pressure drop here is 12 psi, so that will be P1, P2, right? This should be 12. So P2 is given here. So we have all the values. We can calculate this to be okay. We can just substitute the values. If you do this, then you will get 1.38. So does any valve with CV of 1.38 or greater, so we can use a bigger size valve for this purpose. So if CV is less than 1.38 is selected, then the excessive pressure drop will occur over here. So the P1, P2 will be bigger. So this will lead to system malfunction. However, selecting a CV that is much greater than 1.38, so if you choose CV to be much greater than 1.38, then you will have an oversized valve, which increases the cost of your pneumatic system. So this is something that you need to think about. You should also think about scalability. Maybe you may want to increase the scope or the capacity of your system. So you may increase CV to be much bigger, to be slightly bigger, but this is up to your decision. Okay, everyone, thank you very much for your attention. See you next time. Assalamualaikum warahmatullahi wabarakatuh.